Now, free fall is that feeling that human beings are not too comfortable with. If you've ever jumped on a trampoline or jumped off like a platform at a swimming pool, you know what it feels like. And it is weird to just be falling freely. As you fall, you're being accelerated towards the earth due to a force called gravity. And there is some air resistance, obviously, and that would be like friction in the air. And in this course, we ignore the air resistance. Okay, so you guys can ignore the air resistance. Now, if you fall from like an airplane and you are falling for a long time, you'll actually stop accelerating. Does anybody know why? Yeah, you reach something. You know what it's called? Yeah, maximum, but there's another word for it. Starts with a T. Yeah, terminal. Terminal velocity. In the sense that like it terminates. Terminal. So that's what happens. Like in the next unit, we'll talk about this. Like if you're jumping out the airplane, imagine you're the dot. There's this force that acts down on you called gravity, and there's a tiny bit of air resistance that might oppose that force, and you might fall faster or slower depending on how much air resistance there is, maybe how thick the atmosphere. Eventually, though, there's so much air resistance that it actually matches the downward force, and those forces cancel, and then you don't accelerate anymore. We'll never talk about that in this course. When I say, or if you ever see this word, dropped, or if you see free fall, then you're going to have to solve it like how I demonstrate in the lesson today. So here's your notes. Basically, you're looking for that keyword dropped. This 9.8 meters per second square, it acts down, usually, if that's your proper reference. Like if you're the reference point, you fall down. Everything always falls down towards the center of the earth. It's always down. But sometimes you can omit the negative and just make the math a little bit easier. And this acceleration is always constant near the Earth's surface. Now it does vary from like 9.81, 9.82, 9.80, but you can just use, in this course, you're always going to use this one, 9.81. Okay, you always use that one. It's on your data sheet. Even if objects are thrown up or down, the acceleration is still constant. Yeah, so like whether I throw that pen up in the air, or if I throw it down, okay, you always have the Earth's gravity. Now if I apply an extra force, obviously it might accelerate faster than if I just drop it. Okay, so if I supply an extra force, you'd have to consider that. Okay, and your initial velocity doesn't affect how fast you accelerate. So all objects will accelerate at the same rate. This is like a common puzzle that you might see. It's like a thought experiment. You'd be like, if you have a feather and a stone, and you drop them, when do they hit the ground? Do they hit at different times or do they hit the same time? So if there's air resistance, they'll hit at different times because the stone has way less air resistance than the feather. But if it was a vacuum and there was no air resistance, would they hit at the same time? Yeah, they would. So all objects will accelerate down at the same rate. And that's if you ignore air resistance. All right, so let's try some of these. Okay, so we have an iPod being dropped from the top of a tower, and they want you to determine its velocity when it smashes into the ground, and of course you ignore the air resistance. Okay, so like always, you should be dropping your known values on the left here. So like this 45 meters, we have some distance that it's going to drop. Now if you think of this in terms of displacement, you kind of have to have a reference point for displacements, right? Like, how would you define my position? Where am I? Well, if the reference point's the door, I'm left of the door. But if the reference point's my computer, I'm right of the computer. So a reference point is key. So you might want to draw a little picture. There's my tower. It's not very straight, but that's a tower. So where could I drop a reference point? Probably from where the object begins. Would you agree? Yeah, I would throw a reference right where the object's going to start. And then the object falls this way. So that 45 meters is below or above the reference point. Below. So this is actually a negative 45 meters. Now for free fall, if you think back to this equation we were working with yesterday, VIT plus a half AT squared. This one works out just beautifully for the same reason that it worked out in the previous days. Because if you are holding an object and then you just let it drop, what was its initial velocity? 0. And that really just simplifies things. So then you get displacement equals a half AT squared, since VI equals 0. And then really it's just a dream after this. So if I put in my negative 45 displacement, and I got this 1/2, what do I put in for my A value? Do I put in 9.81 or do I put in negative 9.81? Because it's the vector is pointing downwards, right? And then you can solve for t squared. So I'll just demonstrate this on the whiteboard. You don't have to put in the negatives. Like, what's going to happen to those two negatives in the math? They're going to cancel anyway. So you can think of this. Yep, there's no air resistance. The negative has nothing to do with the air resistance. And I'll just, like, what if we just kept things positive? Okay? Then this is my the reference point's the ground. It's like I'm accelerating to the top of the tower and the acceleration vector points up. Would that be the exact same thing? Mathematically, yes. So to solve these free fall problems, like, you don't always have to put these negatives in. Because if you just thought of a situation where I just did the everything accelerates up. Reference is down here. Things are positive now. So it's all about where you put your reference point. Okay, so anyways, these negatives will cancel. Times by 2 on both sides. Times by 2 on both sides. What does that do? Gets rid of the half, right? The negatives cancel because you got a negative on both sides. Just divide out a negative 1. The negatives cancel. How do I isolate for that t squared? And divide out the 9.81. Gets rid of that. And then how do I get rid of that square? Square root all that. So you gotta you just gotta go 2 times 45 divided by 9.81 and then take the square root of that. So I got, did you guys get this? 3.03? So algebraically, I know some of you still need practice with this kind of stuff. When you look at this equation, there's no pluses, there's no extra terms, there's no plus a whole bunch of other crap. So you don't have to do any initial subtracting or moving stuff left and right across the equal sign. You don't have to do that. You just have to do some cross multiplying, like bottom right 2 goes top left, top right A goes bottom left, and then you guys know how to get rid of squares because you do so much work with Pythagoras in junior high. Okay, now what's the difference on this guy? Second iPod is throwing down. Maybe this guy doesn't like his iPod. Okay, so draw a picture with me. You got the reference point. This displacement is negative 45. If this is the object falling, it has an acceleration vector that points down. So your acceleration vector, oh no, sorry, that's my bad. Just copying numbers down, not thinking. Acceleration vector is of course due to gravity. But there's an extra velocity vector vi to start you off, which is 4.5 down. So this thing's moving down. Yes, dear. Oh, really? So if you want to find the velocity, you can use this one. The vi is 0, right? So that goes away again really nicely. And then you got 2 times 9.81 times that displacement. Square root it. Guys see it? Get rid of that. Okay. So a second iPod is throwing down. So here comes the problem when you use this d equals vi t plus a 1/2 at squared. If you wanted to find the time for this one, you throw in your knowns. You got a minus 45 meters. You got a minus 4.5 t plus a 1/2 negative 9.81 t squared. This one you cannot just solve by square rooting. You would have to simplify and then use your knowledge of quadratics, which unfortunately not everybody in this room has expertise in because you haven't finished Math 20. Okay? So you have to come up with different strategies. Yes? Yeah. So I'm just throwing this out there. Like you also in your homework, you'll have to find time, and I'll show you how to do the velocity. It's the exact same as that equation up there. So, ladies and gentlemen, if I'm just saying this, if you're asked to find the time, and vi is not 0, and you try to use this formula, this is a second degree polynomial, and you have to know about quadratics. Okay, so if you haven't taken Math 20, you cannot go that route. So if they don't give you time, the only one that you can use, and this is a must, you got to know this, if you don't give you time, you got to use this one. This vf squared, vi squared, and 2ad. Okay, so we go vf squared, vi squared plus 2ad, because time unknown. Plug in what we know. negative 4.5 squared plus 2 negative 9.81 and negative 45. And again, what is happening with these negatives? The VI, what happens when you square a negative? What happens when you square a negative? Yeah, because the negative times the negative is positive down here. And then here, the same thing. So this is all going to come out positive. So could you have gotten away without using sign? Yes. Because in a sense, you could just think of it like being thrown up and accelerating up. And it's sort of equivalent. Now you just have to square root this result. Okay, so I got about 30.1. You guys get this? Plug it in, please. See what you get. Do you guys get the 30.1? So if you have the nice Texas Instruments, you could actually just type that in exactly how you see it. So they got the VF of 30.1 meters per second. Now just remember that final velocity, again, velocity is a vector, so you can't be just leaving your answer 30.1. What do you got to attach to that? Very nice. Very nice. Remember vectors? Yeah, vectors have two components, magnitude and direction. So a vector is not fully described until you tell me how much and which way. And then a lot of students get this confused too. Okay, so let me throw this pen down to the ground. What's its final velocity? You want to say 0, right? Because it's not moving anymore. But what I'm interested in is like if I throw it down, it's got like 5 meters per second right when I release it. And then I want the speed right the moment right before it hits. That's the final speed, like that 30. Like obviously when it hits and it's going 0, but it's right before it hits. That's the final speed. That's what they mean. Did you guys get that? Yeah. Because you're accelerating over this time interval, right? Accelerating, accelerating, picking up speed, picking up speed, picking up speed, and I want the final speed right before impact. And then when you hit, I mean obviously you're 0, but we're not interested in 0. That's not interesting. So hopefully you can sort of memorize this strategy. I'm not given time. I have to use this. And if they still want me to calculate time, people, just go to this one now. This simple one right here, right, Frank? This one right here. I'm not given time, but if they want me, jump into this one here. So I'll sneak down in this corner and do that. The T and the A will cross multiply switch. Now let's be careful here. What was the VF? 30.1 down, right? So then you put in this. That's the VF. And this is where students, this gets a little bit messy for them because they don't take the time and consideration into thinking about the direction. And the VI was what? 4.5 down, so you throw in another negative 4.5. And then all these negatives mess people up, so you got to be careful. And then of course your acceleration is down as well, so you have a negative down there. So a negative 30, and then you're going to go minus minus, so that pluses. So it's like negative 20 something, 25 or 26. And then you divide it by about negative 10. So the negatives cancel. Why is that important? Could time ever be negative? No, time always goes one direction. So the negatives have to cancel. And it's about 2.5, right? 2.6? 2.6. It's about 25 divided by 10, roughly. You guys feel okay about that? Where it gets challenging is the sign. So la-di-da. I think we're good to take a pause. Let's go take a look at question 24 in the workbook.